Hi there, welcome to this lecture series on matrix algebra. This is lecture 10, part 2. The topic is linear combinations. In part 1, we covered the definition of a linear combination, and we used that to define a concept of linear dependency or linear independency. Now, in this part, we will look at using them to form a basis of a vector space. So let's get started. Let's begin with basis and let's have a definition. The definition is the following. So, a set of vectors, v1, v2 to vn, there are n of them. We say that it is a basis of a vector space V if the followings are true. So I need two conditions. One, these vectors are linearly independent. And two, these vectors span the whole space, meaning V here exactly equal to the span of v1, v2 to vn. Now, one word about English. So you might have noticed that here we wrote basis and here we wrote basis. So basis is a singular noun and the plural of that will be basis. Okay, they sound almost the same. It's confusing. Okay, so just for your information. Now let's take some examples. Example 1, I have two vectors. These are like, you would call them unit vectors. So the first is 1, 0, and the second is 0, 1. And we claim that these two vectors forms the basis of R2. So to show that these two vectors forms the basis, there are two things to check. One is that they are linearly independent. And it is easy to see that they are linearly independent because they are unit vectors, and we have covered that. Now part 2, we need to show that the span of, if I span these two vectors, and they will form exactly R2. So in other words, any vector in R2 shall be able to be written as a unique linear combination of these two vectors. And in fact, we can easily show that. For a vector has element a, b, which is in R2, and then we can write it as a unique linear combination as a times the first vector here and b times the second vector here. Okay, so a similar example would be looking at 2 by 2 matrices, the vector space. Okay, so then we can single out 4 special matrices, and 1, 2, 3, 4, where they are all the elements are 0 except in one position. So the first one is position 1, 1, that's position 1, 2, and that's position 2, 1, and this is in position 2, 2. And we say that they form a basis of the space of all 2 by 2 matrices. Okay, so again, 2 steps. One is to show they're linearly independent, and I leave that as an exercise. And then second, to show that they span the vector space. And this means that every matrix A, B, C, D as its element can be uniquely written as a linear combination of these 4 matrices. And you see that's quite simple. We can form the linear combination by multiply the first one with A, so this position will be A, and then the second B, so this will be B, and so on and so forth. Okay? So therefore, this one is a basis. Okay, so some theoretical result. Let's go through a theorem. So the theorem says that given a vector space V, the following 2 statements are equivalent. Statement 1, the set of vector v1, v2, vn is a basis of V. And statement 2, for every vector little v in V, it can be written in a unique way as a linear combination of this set of vectors. So C1, V1, C2, V2, and Cn, Vn. So when you say two statements are equivalent, you mean that if you assume one, you can prove the other. So we shall be able to prove, assuming 1, I will derive 2, and the reverse, assuming 2, I can derive 1. Okay, so let's give that a try. Okay, let's prove that 1 implies 2, which means if the V's is a basis for the vector space, then I can find a unique linear combination. So this means the coefficients for the linear combination, let's call them C1, C2, Cn, they are uniquely determined. So it seems like our preferred way of showing the proof and often have been to use contradiction. We assume the opposite and we derive something that is absurd. Okay, so on the contrary of that statement, let's say that there are two distinct linear combinations, and we call one with the coefficients Ci, so C1, C2, and Cn. And we have second one, which we call the coefficients Bi's, so there will be B1, B2, and Bn. And both linear combinations give me this vector V, the same vector. Okay, then I can do a subtraction, and then after that I can combine similar terms. So left-hand side becomes 0, and then right-hand side for each V, I will just subtract the coefficient. So I'll have C1 minus B1 here, and then for V2, I'll have C2 minus B2, and so on. So what we have shown here is that now this right-hand side again is a linear combination of the vectors with the coefficients, and the coefficients are Ci minus Bi, right? So for the Vi position. And these two sets of coefficients are not unique. They're distinct, meaning at least one of them are different. So all these coefficients, at least one of them is not 0. So it's not all 0. Okay, and then we concluded so far with our reasoning that this combination, linear combination, will give me 0. Okay, so now remember, the set of vectors v1, v2, they form a basis, and therefore they're linearly independent. And that means that the linear combination that will give you the 0 vector would be the one where all the coefficients are 0. So that means all these coefficients must be 0, and that means C1 equals B1, C2 equals B2, and so on and so forth. And that means the set of coefficients for all the Ci's and the set for all the Bi's, they are the same. And that is a contradiction to the assumption we started with two distinct combinations. Okay, and therefore this assumption is false, and therefore the coefficients, they are uniquely determined. Okay, so to complete the proof of the theorem, we need to still prove the other way around. That is, the statement number 2 would imply number 1. So here I repeat the theorem again in case it has faded in our memory. So what does it mean? The 2 is that if every vector u in V can be written in a unique way as a linear combination of this set of vectors, then this set of vectors is a basis of V. Okay, to show that this is a basis, and let's recall the definition we give for basis. And there are two things there. One is that this set of vectors, they have to span the vector space, and second, and they have to be a set of linearly independent vectors. Okay, let's check both. So first we want to show it's the span. So that is easy to see because from this statement we can see that for every vector V, you can find a linear combination for it using these vectors. And therefore, you span the vector V1, V2, Vn, it's the space V. And second, we need to show they're linearly independent. Okay, so let's say if I want to obtain the zero vector, I see that I can choose all the coefficients to be zero, which will give me the zero element. And then is that the unique way of doing it? Yes, because condition 2 says if you find a linear combination, that is the unique one. So therefore, this will be a unique linear combination to obtain the zero vector. And that implies the set of vectors are linearly independent. And then we reach conclusion 1. And therefore we now completed the proof. Okay, so we now take some examples just to get ourselves familiar with the concept of basis. And okay, now we have two vectors, V1 and V2, which is 2, 1 for V1 and V2 is 1, 2. And we want to show that they form a basis of R2. So we need to show that every vector in R2 can be uniquely written as a linear combination of V1 and V2. And let's verify that. Okay, so let's say a linear combination we call the coefficients x1 and x2. And then B1, B2 is a linear combination with these coefficients. And if you add these two terms up, you will get a vector. The first element is 2x1 plus x2, which is here. And the second element is x1 plus 2x2, which is here. And then we want to find x1 and x2 such that this would equal to B1 and B2. And if we can show that there is a unique solution for x1 and x2, then we're done. Okay, so let's write this up. So I have the first equation and the second equation. And then I can write the left-hand side as a matrix times the unknown vector. So the matrix will be the coefficients 2, 1 and 1, 2, which is here. And the right-hand side is the given B1, B2. To solve this one, well, we know that the solution here would equal to the inverse matrix of this multiplied by this vector. And we can find the inverse matrix, which is a unique inverse matrix, and then equal that. Okay, so there is a unique solution for x1 and x2, which is this, for every given vector with elements b1, b2. And therefore we conclude now v1, v2 form a basis of R2. Okay, one more example. Let's take another set of vector, 2, 1 and 1, 5. And we want to show it's also a basis of R2. So we can go through a similar argument. We want to show that every vector B can be written as a unique way of a linear combination. let's say the coefficients is x1 and x2 for that linear combination, and we have this equation. And if we write out each element in this vector, we have a system, the first one and the second one, with two equations. And you can verify that this has a unique solution. Okay, so we have solved these equations many times, so I'll leave that as an exercise on exactly finding the values for x1 and x2. Okay, one more example in R2. It's an example where we want to show that this set here is not a basis of R2. And there are various ways one can show this, and any of the conditions for a basis can be used to verify that. And another way would be, we can show that these two vectors, they do not span R2, meaning that there are vectors in R2 that cannot be obtained by linear combination of these two vectors. Okay, let's try to show that. Okay, let's give a vector b and 0 and 1. And the linear combination of these two vectors with coefficients x1 and x2, you will see that the second element, no matter how you choose your x1 and x2, will give you 0. It will never be 1. So therefore, there are no values of x1 and x2 that will satisfy this equation. So another example, let's pick 3 vectors in R2, and we say that this set here, 3 of them, is not a basis of R2. Okay, so here we can show that the 3 vectors are not linearly independent, and they are linearly dependent, actually. If that's the case, then they cannot be used as a basis. So let's check on that. So indeed, I can see that if I take the first vector plus the second vector, subtract the third one of those vectors here, I get a 0 vector. So meaning if I choose coefficient to be 1 here and 1 here and -1 here, and this linear combination gives me a 0 vector, and the coefficients here are not all 0, and therefore this set of vectors is not linearly independent and they cannot serve as a basis. Okay, so that's all for this lecture, and next time we will look at dimensions of vector spaces. Okay, so I hope you enjoyed today's lecture, and I'll see you next time.